is going to be of use to you. Let me switch over here. Are there any questions so far? You doing okay?
I think the whole page, the graphic thing, because I'm not for for Google Sheets. How do you make like the whole page to graph instead of just like?
Oh, that doesn't really matter. When you create your graph, it probably produces it first like in a little box on your sheet. There'll be an option in the upper right-hand corner. You can click on that, and one of the options will say Move to Own Sheet, and it will just take the graph and pop it down below into a new sheet. That's not a requirement, of course. That's just something that you can do if it's of use to you. All right. So I'm gonna go back and share my screen with you, the Pear Deck. And I'm gonna move back a little bit here, really move back to what we did, or what you did on Monday. Because what we need are the critical values. There they are. Can you see those okay on your end? So there were, if I remember correctly, 7 pairs of data that came out of the simulation that were on my data table. So I need the degrees of freedom. So with 7 pairs, the degrees of freedom will just be 7 minus 2. So I'm at 5. Move over, and it looks like, I better bring my pen up again. My critical value for R is 0.754. Now remember, I wrote it down so I wouldn't forget. My calculated R value was 0.89. Okay. Well, part of your statistical analysis, right, in this case is to pose a null hypothesis. We did some practice around this last week, right, where a null hypothesis is a really simple statement that there's no relationship, no effect, no correlation, there's different ways to phrase it, between the variables that you're comparing. And what biologists, really what scientists do, is they're not ever trying to prove hypotheses, because that's literally impossible to do. There's always this possibility that chance, that natural variation is influencing the outcome of your experiment. So this idea of proof is really a misnomer in science. If you've ever heard it, if you're still using it, I would encourage you to try to let that go. It's not a thing, it doesn't exist. Instead, what scientists are trying to do is disprove null hypotheses, and as a consequence, generate support for the alternative hypothesis, that there is a relationship between the variables that they're comparing. So in an analysis like this, we calculated R at 0.89. We're going to compare that value to the critical value, 0.754, and obviously 0.89 is greater than 0.754. And because of that, that's going to allow us to reject the null hypothesis, that there isn't a relationship between those two variables, right? And instead, we can support the alternative hypothesis that there is a relationship. And that's the evidence section for this particular lab, right? You've got your data, you've got your graph, you've got your value of R, you find your value of R crit, you've posed your null hypothesis, and you ask the question, can I accept it or can I reject it? Right? In this case, you can reject it. And then your claim will follow from that, right? There is a relationship between these two variables. There is not a statistically significant relationship between these two variables, depending on where your analysis leads you. And in your explanation, you're coming back and you're connecting the science idea, which you can always find in the slide deck that I attached to the assignment. I think in this case, it deals with the transmission of information and how that transmission of information promotes changes both within and between biological systems, to the evidence. Okay. So does your analysis support the claim that information is being transmitted? Well, that depends on how you set up your experiment. And you're not trying to say that there is a relationship, nor are you trying to say that there isn't a relationship. That's not science, right? Science doesn't always have the answers. We're trying to find the answers and then generate evidence in support of the answer, ideally to convince others that we're onto something. It's one of my great fears that your experience in high school has been to verify something that is already known. And while that has merit, it can't be your entire experience. Because if that were the case, why become a scientist? I mean, you just spend your entire career verifying what we already know? Why? So, that was a lot of me talking. What questions do you have before we move forward?
So was it okay if we used something that did not reject the null hypothesis in our thing, our lab thing report? Or
So Larry, I wanna push on that question a little bit, right? How would it not be okay? And you don't have to answer that, right? But where, help me, not just Larry, anybody, help me understand where that question is coming from. I think it comes from this conditioned behavior, right? This conditioned response that, well, of course, we're trying to find the answer. And we're trying to find out how close our answer is to the actual answer. Okay. But sometimes in science, we don't get the answer that we're looking for. Sometimes we've asked questions that have never been asked before. So we're generating evidence and we're testing our evidence statistically to build support, to strengthen our claim. That's the scientific process. Of course it's okay if you have to accept the null hypothesis. Of course it's okay if you get to reject the null hypothesis. It doesn't matter. Both are equally valid. All right. What other questions do you have before we move on? Was this helpful? Kind of helpful? Can you give me a thumbs up if it was helpful, thumbs down if it wasn't? I won't be offended, it's okay. Thank you, digital thumbs. Okay. So just to circle back, right? If you need to add this to your lab, feel free to do so, right? We're not doing what we do in class. We're not spending the limited amount of time that we have together to then not use it in something like a lab write-up or an assessment. Okay, so if you find yourself wondering, am I supposed to be doing that? The answer is probably yes. And if you're not sure, ask. Please ask. It's okay. That's why I'm here. If you knew everything already, you'd be me. He says sarcastically. Number of pairs is just the number of data points, right? So you probably manipulated the IV and you got a dependent variable that you were able to measure in the simulation. That's one pair. Second pair, change the IV again, get a change in the dependent variable. There's a second pair. Third pair, fourth pair, fifth pair. I think I recommended 5 pairs of data. I made the video a while ago. I don't remember exactly what I said, but 5 is a pretty good place to start with. I may have included 7 data points, but that's just because I'm a nerd and I like data. All right. Now, okay, is it okay to move on? Because really the rest of the lesson today is another form of statistical analysis. Different, but important as we think about our data and we think about how to analyze our data in future lab experiments. So I am going to move to our agenda slide once again. I think based on the time that we just spent going over the correlation coefficient analysis, we're going to skip our check-in. We'll do it again. It was a scavenger hunt in your own homes. So we'll do that again some other time. And we'll move on to the statistical test, this new statistical test, which is different from the one that we just talked about. And along the way, of course, we'll take our break, and I've got some practice problems that we can work on both together, and then hopefully you'll have some time to work independently on some AP practice problems, both multiple choice and free response, I believe. But we'll see how things go. All right. So this graphic probably looks familiar to you. The other day, or really just now for that matter, we followed a line. Here, let me draw on it. We followed a line that led us down this path to the linear regression test, where we calculated R, we compared it to our critical value, and based on that comparison, we were able to either accept or reject a null hypothesis. But that analysis was dependent upon a particular type of data. It was dependent upon continuous data. If you might recall, that continuous data is just data that's being collected over the course of time, right? So it's probably the most familiar type of data to you. Going back to physics, distance versus time, velocity versus time, any of the work that we've really done this far in first quarter has been continuous data. But there's another type of data. It's discrete or categorical data. And if you've had a chance to do the homework for today, you've already read a little bit about this, maybe you've even practiced with it already. Discrete data really can be thought of as counts of something. So it's not going to be frequencies, it's not going to be percentages, it's not going to be even means of values. It's going to be literal counts, observations of particular phenomena. Okay, so it's a different type of data. If you prefer, you can think about if continuous data is occurring across time, discrete data is occurring at a moment in time. Okay. Let me pause there. Does that bring any new questions to light for you?
What kind of situation will we use this in?
All sorts of situations. So for example, if you went back to lab number 5, you might have asked yourself, why am I not analyzing these data statistically? Well, it's because frequencies, right? Since you knew the population size, can actually be, you could actually calculate the number of individuals of each genotype, for example, that existed in your population after 50 generations. And you can use this chi-square test to analyze those types of data. So literally the number of individuals that are present at a particular moment in time. The sample problem that we're going to work with is another animal behavior example. It's going to use fruit flies as an example, where you count the number of fruit flies that are or that have moved towards a food source, or those that have not moved towards a food source. And through that count of the different number of flies in each of those two environments at that particular moment in time, you can determine whether or not there's a significant difference between the number of flies in this area compared to this area. So close to the food source versus away from the food source. Okay, so this is where this new test, this new statistical test comes into play. We're going to use discrete data, so observations, or the number of observations, the number of organisms, the number of occurrences, right, at a particular moment in time, to determine whether or not there's a significant difference between whatever it is that we're comparing. All right, so it's a different type of analysis. So the formula is very simple. It will always be given to you. You do not need to memorize the formula. And where things get a little bit tricky as you first get started on this is that the computation, we'll go through the computation together, is not going to be hard for you. But it's the O and the E that are going to be challenging. The O stands for an observed number of measurements or observations or organisms, okay? The expected is also going to be a number of occurrences or observations or organisms, but it's going to be based on what you think, what you hypothesize to have occurred during the experiment. And the observed values are what you actually saw. So ultimately, what you're testing is there a significant difference between what you would have expected and what you actually observed, right? That's what this test is going to allow you to do. So the expected values are often going to be based on your null hypothesis, right? Because that's what you want to either accept or reject. And you might say something like, well, there isn't a difference between the observed and the expected values, right? So you'll set up your expected values accordingly. Again, we'll do a practice problem here in just a bit. And then you'll actually do the experiment and you'll get your observed values. And through this computation, you'll be able to determine whether or not there's a significant difference between what you would have expected, often based on your null hypothesis, compared to what you actually observed when the experiment was conducted. All right? Let me pause there again. Questions? All right. Here's the good news. Once you have this chi-square statistic, the way that we do the analysis is just like we do the analysis for the correlation coefficient. We're going to get a calculated chi-square value. We're going to look up a critical chi-square value at a particular number of degrees of freedom. And we're going to ask the question, is the value that we calculated greater than or less than the critical value? So you'll get a table that looks like this. You do not have to memorize it ever. Please don't try. That's a waste of your cognitive energy. But you'll get your calculated value, you'll compare it to the critical value, and then you do what you've done last week. If the value that you calculate is less than the critical value, you have to accept the null hypothesis. There is not a difference between what you would have expected to occur during the experiment and what you actually observed occurring during the experiment. If the value that you calculate for the chi-square statistic is greater than the critical value, you get to do the opposite. You can reject the null hypothesis. You can accept the alternative hypothesis that there is a difference, right, between the expected and the observed values. Okay. So that part is going to be the same. So I have 9:29 on my clock. I am talking a lot. I want to get up and move. Maybe you do too. So this seems like a good time to take a break before we dive into the practice problem. Let's do 3 minutes. We'll come back together at 9:32 and we'll begin to explore how to use this tool, this analytical tool to analyze data. I'll see you in a couple minutes. All right, if we could start making our way back together, please. And as I can't see if you're there or not for many of you, as you come back, if you'll read the scenario, the question that's currently on the screen, we'll use this as our practice problem to work through together. If you'd like to type something in the box, you're welcome to, or the boxes, but we'll use this as a practice problem to go through together. So before we get started, well, first off, do you need some more time to read? Or are you ready for the next step? Give me a thumbs up when you're ready. No rush. Take your time. You don't need to write anything. We'll go through this problem together. If you want to write something, you're welcome to. Are we ready? Thumbs up if you're ready. Not seeing a lot of thumbs. I'll give you a little bit more time. I'm seeing a few more. Thank you. I just don't want to rush you. Okay, what clarifying questions do you have about this problem before we get started? Can you picture how this experiment was set up? This is actually an experiment that we would have done in class with actual fruit flies, living fruit flies, but unfortunately we can't.
Is the chamber just like, wait, never mind.
I think I have a picture of the chamber in here. I thought I did at least. Maybe I don't. Well, maybe I don't. Imagine that you kind of have two arms with a central chamber in the middle. So you load the flies into the central chamber. And then at the end of either arm, you'd have this cotton ball, one that has the glucose solution and one that's dry. So once you put the flies in the middle, they can freely move to any of the two arms that they like. Okay. And the question, or early at the end, what they tell you is that every minute you're counting the number of flies that are on each side of the chamber. That's all it is. So going back to the discrete data, right? These are counts at a moment in time. Yes, we collected data for 10 minutes, but you're doing a count of the number of flies every minute for those 10 minutes. Okay. All right. So, the prediction would be pretty simple. You might say something like, I predict that a majority of fruit flies will be on the side of the choice chamber, which includes the cotton ball soaked in glucose solution because flies, oops, are attracted to glucose as a potential fix. Sorry about that. Food source. Like that. These are fruit flies after all, right? They're going to feed off of decomposing fruit in nature. And as fruit decomposes, it could break down into simple sugars, and that might be what you're actually trying to test. Okay. So the prediction is not going to be anything complicated. Honestly, that's the second box over here on the right. It's really an experimental design question. It doesn't have much to do with the chi-square analysis. I'll say quickly that if you've got a cotton ball with glucose solution on one side of your chamber, but a dry cotton ball on the other side of your chamber, it's a pretty crappy experiment. What could you easily do to remedy that? Cotton ball soaked in glucose solution on one side, dry cotton ball on the other. Will be a quick.
Maybe you could do water, or is that weird?
No, it's not weird. It's spot on. Thank you for sharing that, Jordan Cole. Yeah, if you have a dry cotton ball on one side, but a moist cotton ball on the other side, you actually have two variables in play. You've got glucose, or the presence of glucose, plus the presence of moisture. If the cotton ball is dry on the other side, you don't know whether or not it's the moisture or the glucose that's attracting the flies to that end of the chamber. So it's a really poorly designed experiment to have a dry cotton ball on the other side. Yeah. So you have a much better control setup. All right, but enough on that. Let's go to the actual analysis here. Get rid of this. All right, so again, give yourself a moment to read this next part of the problem, because this is the actual chi-square analysis part of the problem. When you're ready, once again, give me a thumbs up. It's okay if you're not sure how to solve a problem like this. That's why we're doing it together. If you've done the reading, if you've tried the practice problems for today, you might have a head start, a jump on others. That's okay. If you didn't have a chance to, that's why we're doing this. I saw quite a few thumbs. I'm hoping that that means it's okay to move forward. So we need to perform a chi-square test. Okay, and to do a chi-square test, we're actually going to build a chi-square table. And that table is not something that is complex to set up. In reality, what it's going to have is a few columns. It's going to have an observed column. I usually use O for observed. It's going to have an expected column. It's going to have an observed minus expected column. It's going to have an observed minus expected squared column. And then finally, it's going to have an observed minus expected squared column divided by the expected. Okay. And if I were to go back to the actual formula for the calculation of the chi-square statistic, you're probably going to see why we're doing that. Right? That last column, observed minus expected squared divided by expected, well, there it is. What we're going to do once we have all these values, for all of you Greek scholars out there, the Greek letter sigma means sum. So once we have all those values in that final column, we're going to add them together. So as I set up those individual columns, I'm kind of doing a step-by-step process that I can use to actually sum all of those values together at the end of the process. All right, so moving back, whoops. All right, so we are gonna focus on the 10-minute time point. So again, remember, it's discrete data. It's categorical data, right? It's at one moment in time. Do not be tempted to start averaging the 1 and 10-minute time points together. That's not, that's continuous data, right? We're not trying to do that. The categories that we're working with, well, if I were to pull up my pen again, we've got ripe as a category. We've got unripe as a category. And it looks like we've also got a middle area, right, where we loaded the flies into the chamber in the first place. There's always a chance that after we loaded those flies, they didn't actually go anywhere. So we have to account for the number of flies in that part of the chamber as well. Well, we're focusing on the 10-minute time point, and these are our data. These are our observations. Those are the numbers that are going to go right in that observed column. So for ripe, 10 minutes, I've got 45. For unripe, I've got 12. And middle, I've got 3. Is that okay so far? I can't see you, so I literally can see 3 of you right now. It's a very disequilibrating to stare at just white text on a black background. I can't see your eyes. I can't see your bodies. So it helps me to know that it's okay, just with a simple thumbs up. Thank you, Toby. Thank you, Nick. Thank you, Olivia. All right, the expected values. These are the ones that can give people fits, right? But for an experiment like this, right, if you posed a null hypothesis for this experiment, your null hypothesis would probably be something to the effect that flies do not exhibit a preference for ripe banana versus unripe banana. Simple, right? They're not showing, right? They're not moving to one side of the choice chamber compared to the other, right? There's no difference. There's no relationship. So really what it comes down to is, okay, well, how many flies do I have total? Well, 45 plus 3 is 48 plus 12 is 60. Biologists can do math too. And if I don't expect there to be a difference, a preference for these fruit flies in terms of ripe banana versus unripe banana, I might say, and this is one possibility, I might say 30 and 30, which means there's 0 flies in the middle. And you can do the problem that way. There's nothing wrong with approaching the problem this way. Is there another way we might have approached it?
You could have expected the fruit flies to like a ripe or unripe banana.
You could, but you don't necessarily know how many flies would like or not like. So if we come back to the null hypothesis, if we base our expected values on the null hypothesis that they don't have a preference, right? That the same number of flies would be on either side of the choice chamber. We've addressed the ripe versus unripe with 0 flies in the middle, but what I would encourage you to consider the possibility of, right, is that some of the flies that we loaded into the middle stayed in the middle. And if we think of this as having 3 regions, right, a ripe side, an unripe side, but a middle, you could feasibly have something like this. 20, 20, and 20. Either of those 2 approaches will work. Okay? This is not about the answer, it's about an answer. Is it okay if I use the 20s, or would you prefer 30, 30, 0? If you want 20s, give me a 1. If you prefer the 30, 30, 0, give me a 2. It's like split. Again, you can put it in the chat if you have a preference. It helps me. It helps me see. If I can't see you, this is really the only way that I can see you. Okay, I saw more 2s than 1, so I'm gonna go ahead with the 2s, and I'm gonna use the 30, 30, 0. But again, it doesn't matter. Either approach would work. All right, so the math is going to be pretty simple. That's 15. That's actually negative 18, right? And 3 minus 0 is 3. 15 squared, 225, right? No. Calculator people? Yeah, 225, look at that. 18 squared, that's 324. 3 squared is 9. And then it's just that value divided by the expected. So 225 divided by 30, that's 7.5. There's a decimal point there. 324 divided by 30 is 10.8. This one's going to be funky, right? 9 divided by 0 is an undefined value. You can't add an undefined value, so it's okay just to assume that it's 0, right? So remember, the formula is asking us to sum those observed minus expected squared divided by expected values together. So 7.5 plus 10.8 is 18.3. Okay, that is our chi-square statistic. So what we need, right, are critical values. Whoops. Okay, here's our table of critical values. Still going to use our 5% threshold. Our probability due to chance of 5%, or P, is 0.05. Degrees of freedom are calculated a little bit differently this time around. It's the number of categories minus 1. So we've got ripe, unripe, middle, 3 categories. Minus 1 would be 2. So we want 2 degrees of freedom. We can stick with that 5% probability due to chance, due to natural variation. If you want to be more stringent, you can, but you don't have to. So it looks like our critical value is going to be 5.99. So chi-square crit is 5.99. And I bet you can see already 18.3 is greater than 5.99. So if we had posed a null hypothesis, there is no significant preference in fruit flies for ripe banana compared to unripe banana. That works, right? There's no difference, there's no relationship, there's no effect. You can phrase it however you like. With a value, a calculated value that's greater than our critical value, what can we do with that null hypothesis? Can we accept it? 1, reject it? 2. Or chat works. Thank you, Phoebe. Thank you, Sophie, Isaac, Toby, Larry, Olivia. Right, we can reject it, right? We can reject the null hypothesis that there is not a preference and instead accept the alternative hypothesis that there is a preference, which you may have already seen, right? Just by looking at the data. 45 versus, I guess, 15 on the other 2/3 of the chamber, okay? But this is a way to verify that claim statistically. We're not just saying this number is bigger than this number, stop. We're saying, yeah, that number is bigger than this number, and that difference between the numbers is statistically significant. It's not due to chance, it's not due to natural variation. These flies are just randomly moving into different sides of the chamber. They're moving onto the ripe banana side of the chamber in a way that is significantly different than the way that they're moving towards the other side of the chamber. So we've actually got our calculations for the chi-square table over here. right? And this is really the comparison that we're making. 18.3 is greater than 5.99. So we can reject the null hypothesis. So I want to respect the time that we have left. What questions is this bringing up before we transition? Okay. Let's see here. So the scoring guide did the opposite, right? Oh no, we're wrong. We've made a terrible mistake. We've lost all the points. We're going to fail. Our destiny is dropping out of high school, never going to college, never finding a significant other, living under a bridge with the trolls for the rest of our life. That's not what this is about, right? In fact, you can even see down below, expected values must be those predicted by the null hypothesis. Right? If your null hypothesis was like ours, right, that there's no difference between the ripe banana compared to the unripe banana, you're going to end up with 30, 0, 30 there. And when the readers look at your work, they're going to give you credit for that. There's more than one way to solve these types of problems. It's not the answer that matters. It's an answer that you can support with data and a statistical analysis in this case. Okay. But regardless, if you did it this way, you're going to end up with a value that's still greater than the critical value, and you're going to end up making the same claim, the same conclusion. Sorry, go ahead.
I was gonna say, doesn't it say on the bottom that no subs can equal to 0?
I have no idea what you just said. I'm sorry.
Doesn't it say on the bottom that that this says include no subs equal to 0? What is that supposed to mean?
That's if, right, the null hypothesis is different from the one that's posed here. Right? In this case, their null hypothesis was that there was no preference for the flies in any of the 3 regions of that chamber, right? So there can't be a 0 there. But because we assumed, right, in our hypothesis, and I asked you, yes, I was the direction that you wanted to go, that the flies were exhibiting either no preference for the ripe banana side or the unripe banana side, then we had 30 and 30 with 0 in the middle. So it's dependent upon the null hypothesis. Trust me, I've been doing this a while. I know how this works. Okay. All right. So because we spent some time at the beginning of class doing some work with the correlation coefficient, we didn't have a chance to do any of the other practice problems. So I would encourage you, when you have an opportunity, if you haven't done the homework for today, there are some practice problems built into that assignment, but there's also some practice problems built into the Unit 4 notes slides. So I'd encourage you to take a look at those. And yeah, lots of different problems. We might start Monday with some of those problems too. So before you go though, if you could, that was just one practice problem that we did together. If you were right now to assess how much more practice you need, could you drag your dot really quickly? And as soon as you've done so, you're welcome to sign off, and I will see you again on Monday morning. Thanks for being here, folks. Hope this was helpful, at least a little bit.
Have a good day.
Thank you.
Thank you.
Wait, Mr. Bergeron, I have a question on the homework for the second problem. So I understood what the expected values were going to be on the first one because that was easy. It was just 400, 400, and 400. So the second problem, would it be all 400s and then 62? Because it was 1,662 for the jokers.
There's 2 jokers per deck. So if you knew the total number of cards, there's 52 cards in a deck normally, but now there's 54 cards in a deck if you include the 2 jokers. So you'd have to divide the total number of cards by 54 to find out the total number of decks of cards that you're working with.
Oh, okay.
You have the decks multiplied by 2 to have the expected number of jokers that are totally present in all those cards.
Okay. So should I redo it if if it was wrong?
It's practice, right? It's practice.
Okay.
If you know,
Because I didn't know, so I put 400, 400, 400, 400, then 62.
yeah, it's practice. So if you want to do that, you're welcome to, but I'm not going in and checking practice for accuracy. That's absurd. Oh, you froze.
I'm sorry, I keep getting kicked off my Wi-Fi.
I'm sorry. That's
Okay, thank you. I didn't want to leave without saying thanks.
You're welcome. I
Okay.
appreciate it.
Bye.